G'day, Chris here and welcome back to ClickSpring. So with the cutter forming tools complete, it's time to get started on making the gear cutters. And to recap, the first one we're making is a 0.8 module 30-tooth Involute gear cutter with a 20-degree pressure angle and a clearance of 0.25. And we're going to make it from a chunk of this 01 tool steel. This is the flat stock version of the rod material used to make the button cutters, and so it has the same machinability and heat treating characteristics. Now, regardless of the final gear parameters, the multi-tooth gear blanks all start out essentially the same, with some fairly straightforward reference geometry. There's a central hole which locates the blank on the cutter arbor made in the previous video. And then there are 4 equidistant indexing holes that match up to the small hole on the face of that same tool and serve to index the blank. And all of this, of course, is well suited to being formed on the mill. These 4 dots are reference points that serve to indicate the full depth of cut when forming the first features of the cutter, and you'll see how they're used in a moment. Our intention, of course, is that the cutter be formed with precision, so naturally we need to have confidence that as we're forming it, the part is seating and registering correctly on the features that have been created for that purpose. Working against us are the inevitable burrs thrown up from the cutting tools, along with the odd stuck chip. So the reference surfaces and features need to be routinely checked and, if needed, cleaned up on something like this India stone. A light touch with a countersink is usually enough to clean up any edge issues on the holes, and a brush or shot of compressed air can sort out any chips that might have lodged within the holes. Okay, so now let's have a closer look at the cutter arbor from the previous video. The small boss and the front face serve to locate the cutter blank on the tool and maintain what will be a vertical alignment once it's all held in the lathe. And much like the carrier component of the sharpening tool, a pin passes through the blank and into the face of the cutter arbor, locking the radial orientation of the blank and providing a reliable opposition to the cutting force. Much like the sharpening tool, this feature also enables indexing of the blank, so we can lock it in place, take the necessary cuts, index, and then continue around all 4 positions. And a simple cap screw provides the closing force to keep the whole thing together. It's a very simple assembly that permits the blank to overhang the perimeter of the arbor, presenting each side in turn to the lathe tool for cutting as the blank is extended, enabling us to first of all form 4 distinct lobes, and then ultimately to form the cutter profile geometry 1 quadrant at a time. Once the assembly is in the lathe, the cutting tool is set just clear of the work, and the first lobe can be formed, cutting to the reference points that I mentioned earlier. This perimeter cut isn't a particularly critical dimension, but it must be the same across all 4 lobes. So once there, the cross-slide collar is zeroed, and since we're going past that 0 point several times on our way to full depth, I like to put a reference mark somewhere on the cross-slide so I can keep track of where I am. And as I mentioned, the cutter burrs are something that need to be controlled so that we can be sure that we're getting a clean seating. So there are repeated quick stops past the India stone to clean up that rear face of the blank throughout the process. Then, once it's cleaned up, it's back into the lathe, index and repeat. At the end of this part of the process, each lobe should neatly terminate at the reference dots formed earlier, and so this is our first opportunity to catch any significant error in that regard. Okay, so with the lobes formed, we can now look at forming the cutter profile. And for this, we need to align the button cutter with the blank, and then carefully bring it to bear on each lobe while cutting to a specific depth. Starting with the alignment, the calculator provides the numbers that we need. The three key values being the thickness of the cutter blank, the button diameter, and the distance between each button. The button cutter is registered against the face of the blank, and then from here it's a straightforward process of using an indicator to carefully measure each move of the carriage towards the headstock. First, we move 1/2 of the button diameter. Then 1/2 of the distance between the buttons. And finally, 1/2 of the thickness of the cutter blank itself. And with that, the central axis of the button cutter is aligned with the middle of the cutter blank. The cutter is then touched off from the perimeter of the blank, and then returned to the central position with reference to the indicator reading that was just identified. We now have the 0 position for the button cutter in reference to each lobe of the blank, so the cross slide is zeroed and the carriage locked. And although the cross slide dials are perfectly fine to track the next operation, for a cut like this I like to have a dial indicator as a second reference. So I set up the indicator zeroed to the same point as the cross slide was a moment ago and refer to both as the cut progresses. Then it's back to the calculator for the in-feed value and into the cut, with a slow feed rate and plenty of cutting oil. And keep in mind that depending on the blank thickness, you'll likely be cutting air for the first section of the in-feed travel until contact is made with the work. Now for the first cut, I do a couple of quick progress checks throughout the process to confirm that all is as it should be. For example, an asymmetry in the cuts would suggest an error in positioning the button cutter, or maybe that the carriage wasn't properly locked down. If it's caught early, that sort of error can be easily corrected and the work saved. Once at the full cut depth, the work is indexed to the next position and the process is repeated. Now of course this is not the most robust way to be presenting a workpiece to a lathe cutting tool, especially with an interrupted cut. So light cuts are in order, and by light I mean super light with a slow RPM. The very last thing we'd like to see at this point is a chipped edge on that button cutter. For this cut, the lathe is running at about 200 RPM, with less than 1/100 of a millimetre advancement on the tool per cut. Any sort of woody knocking sound requires investigation, because almost certainly a button is chipped or something else is wrong. But if it's something simple like chatter, then it's fairly easy to deal with on the fly. And one of the most effective ways to deal with it is with the lathe power unplugged, to back right off on the cut and then very gently feed in while pulling the spindle through by hand, essentially scraping the chatter print from the work. And that's the hard part of the job complete. Each lobe of the cutter now carries the gear cutter profile. All we need to do now is mill away small sections from the blank to reveal the 4 cutting faces. And this is where our cutter arbor again comes into play. This flat section is designed to permit easy location and gripping on the vise, and it positions the rest of the cutter arbor features where we need them, so that they orient the cutter blank for the next step. Again, the pin serves to index and lock the blank during the cut, and the cap screw gives the closing force. Once again, light cuts are the safest approach, and I tend to do a rough stock removal first across all 4 faces, leaving a small amount of material for a final pass. The spindle can then be locked off for the final pass and the part indexed for each cut to ensure a consistent result across all 4 faces. And that's all of the cutter features formed. Next up is the heat treating. And it's worth noting that this is our last chance to conveniently work the metal in its annealed state. So if the cutter is expected to be retained for any period of time, then we'll need to be able to identify it. And so now is the time to give it some clear identifying markings. Heat treating exposes steel to quite damaging oxidation, something we generally prefer to minimise. By far the most effective defence that I've used is powdered boric acid mixed into a slurry with denatured alcohol. It forms a protective glaze over the part at high temperature, and it's most effective if the part can be kept fully immersed throughout the heating process. Once it's all prepared, the part is brought to a red heat and then quenched in oil. You'll see this old file in several previous videos because it's one that I've reserved for this specific job, to do a simple file test on newly quenched parts. Both the sound and feel of the file as it skates over the surface give a clear indication of the glass-hard martensitic state of the material. Now, after having put quite a bit of time and effort into making it, the last thing I want is to leave the cutter vulnerable to chipping. So for this temper, I'm aiming for something just a little further along the colour scale than the buttons, something like a medium to dark straw. The cutter is still very hard, but most importantly tough, and so much less prone to chipping. A dunk in oil cools it down, and the cutter is now ready for sharpening. A quick thumbnail check confirms a keen edge. And that's the multi-tooth cutter complete. So let's give it a quick first test in something relatively forgiving, just to confirm that all is as it should be. In this case, I'm using 3mm brass stock, turned to the outside diameter given by the calculator. Once the cutter has been centrally aligned on the blank, it's brought down to touch off on the perimeter. And the calculator provides the depth of cut or in-feed figure. And in this case, because brass is such an easily machined material, I'm taking the full depth of cut in one pass, with the cutter running at maximum RPM. Now, of course, getting an acceptable result in brass is one thing, but to have a truly useful system, what we really need to assess is the performance of the cutter in steel. So let's have a look at how things go with a similar sized slice of hot rolled steel. It's not often that I subject you to the tedium of a long duration real-time cut like this, but I'd like you to see a key limitation of this sort of small gear cutter, and that is that they must be treated gently. And this applies as much to the commercially produced high-speed steel versions as it does to this shop-made carbon steel variety. They simply will not tolerate misuse. So that means a modest RPM, somewhere in the range of 200 to 400, and a very slow feed rate. Now, I'm deliberately cutting dry to give you a clear view of the cutter performance, but ideally they prefer a continuous flow of cutting oil to both remove the chips and keep things cool. Another way to preserve the cutters in harder materials like steel is to take a roughing pass to remove most of the stock, leaving just enough on for a second pass as a final finishing cut. And that's what I've chosen to do here. It does add somewhat to the time required to complete the operation, but given the time and effort that's gone into its creation, it's a small price to pay to greatly extend the life of the cutter. Okay, so that's the first look at the multi-tooth cutters. And we'll come back to this with some more detail in the next video on cycloidal cutters. Now, let's have a quick look at an alternative that's often a more suitable option, depending on the nature of the job. And I'm referring to a simple fly cutter. The channel on the front face of the cutter arbor is designed to accept both a fly cutter blank and a small packing strip. And you'll notice that one face of that channel passes through the centre line of the tool. To form the cutter profile, the packing strip is positioned on top of the blank, and then the blank is turned in the lathe to receive the profile geometry from the button tool in exactly the same way as for the multi-tooth cutter. After heat treating, when the cutter is ready to be used, the positions of the packing and the cutter are reversed to give a natural relief to the cutter profile. Heat treating follows, again tempering to a medium or dark straw, and then it's back into the cutter arbor to drive the cutter in the spindle of the mill. Now you might be wondering, given how much less work goes into making a fly cutter, why bother with the multi-tooth cutters at all? And generally it comes down to the time required to take the cut and cutter wear. That single tooth not only takes longer to remove material, but it also takes all of the load, and so tends to wear out faster than a multi-tooth cutter. But for one-off jobs, particularly in soft materials, it's often very hard to beat a fly cutter. All going well, the result from a fly cutter should be no different than that generated by a multi-tooth cutter. And finally, let's have a look at how we can generate a fly cutter to cut a rack gear. Again, the blank is shaped with a packing strip on top, and the key numbers are provided by the calculator. For the first time, we see a requirement to set up for a taper, something that will be a central part of the next video on forming cycloidal cutters. The convenient thing about forming a rack profile is that there's nothing particularly special required of the cutting tool. But one requirement is that it have an acute angle, to enable a clean touch off on the work from either side of the tool. Once the tool is located relative to the work, the cut progress is monitored with a dial indicator to the full depth value provided by the calculator. The process is then repeated for the other side to provide a symmetrical profile to the cutter. Again, the usual heat treating applies and the required values are retrieved to put the cutter to work. Now it's worth pointing out that we could have used the tools to make a multi-tooth rack cutter if we'd wanted to, applying all of the same data and cutting on a taper, but just with a multi-tooth blank instead of the fly cutter blank. But this is an interesting case of how the flexibility of being able to make both single and multi-tooth cutters provides complete flexibility to accommodate the limitations of the available tools. Cutting a rack on a vertical mill tends to be a bit awkward in terms of cutter clearance and reach, especially with the small bore cutters to which I've scaled these tools. But a fly cutter immediately solves the issue and enables as much clearance and reach as required to get the job done. And that's the basic process of making Involute gear cutters in the home shop with these simple tools. In the next video, we'll have a closer look at the process of forming cycloidal gear cutters and cover off a few of the edge cases of each gearing system. Thanks for watching. I'll see you later.